Right.
We can't hear you, Carlo.
Is it all right now?
It's all right now. Yeah.
Yeah. There is either an issue with probably there is an issue with Zoom for Linux because this audio issue comes up from time to time. Although it is very strange because not with every Zoom server. So. For instance, when I use American Zoom servers, there is absolutely no problem. But with British ones, there are. So I don't know why. It is very, very weird. All right. So I was just saying that before we begin, we briefly recalled what we proved so far. So we started proving the Cauchy inequality, which maybe by now we write in the, let's say, in the grown-up form, which is this, in the more general one. So A and B, and this is true in every, so this is true in every inner product space, vector space V. Okay, so by where now we know that actually this is a norm, so we can call it a norm, and that is the inner product. So it is defined, so the norm is defined, is the so-called induced norm from the scalar product. And we actually started by this inequality that is subsumed by this more general form, actually even with weights, and also we saw a version for integrals, but maybe I just recall it here. This was our starting point. Which holds both for finite sequences and for infinite sequences. Okay, then we proved we were about to prove the general form of the AM-JM inequality. I just proved the version, this version, so that the standard geometric mean is dominated by the arithmetic mean. And we were about to say that we can extend this argument, and our time finished, so we resumed today. And our goal is to prove this more general version of this inequality that we can write as follows: that the product, so maybe I write it in extended form first, so the product of a1 to the power p1 up to an to the power pn is dominated by the sum of p I, where for us the pi played the role of weights. Okay, so each pi is positive and the sum of the pi's is equal to 1. And I would leave to you the task of formulating in corresponding inequalities when the weights are not normalized to 1. This is really just a little arithmetic exercise. There is really nothing more than that. I'm just saying that you should do it because we are going to use it in the proof of this more general form when the pi's are just real positive numbers summing up to 1. So I mentioned yesterday that our plan of attack to this problem is first to establish the inequality when the numbers p1 up to pn are rational, and to deduce from that the general case using a very pervasive idea of analysis, which is always to try to do things on a dense subset of a set, and then to exploit continuity, if you have it, of course, in the sense of the larger space. Okay, so in particular, in our case, what would that mean? Why would this plan of attack work? Well, because we see that both sides of these inequalities are continuous functions of p1 and up to pn. Okay, continuous function in the sense of course, real, right? functions of the real variables p1 to pn, so both sides are continuous, then if we can establish this inequality on a dense subset of Rn, then by passing to the limit, we can get exactly the same inequality by just the theorem of the permanence of sign in the limit. Okay. There will be an issue with this procedure that I mentioned yesterday, because whenever we have for now just actually the basic case of weights all equal to 1, we can indeed say very clearly what is the case of equality. And if we pass to the limit, we see that we have an issue, because when you have that a sequence is larger or equal, is larger, strictly larger than another sequence, you cannot say that in the limit you still have a strictly larger sign. You can only have larger or equal. So then we will do it in a, let's say, in an accurate way, in a let's say we could call it a trick in this case, to reestablish the case of equality. So let us proceed anyway. I would like to stress once again that the idea of starting from the natural, moving to the rational, and from the rational to the reals, this is a very common, simple in itself, but powerful idea of analysis in general. Okay, so let us say, once we have this, how do we proceed for the case where, so case 1, where P is Qn. By P, I mean the whole vector P1, Pn. Okay, so I mean this. And we can certainly do the following, that we can identify numbers Ki and natural number Ki, natural number m, such that we can write Pi equal Ki over m, where m is fixed. And of course, since we have, so we establish first the case where the sum of the P1s are equal to 1. So we can always do this, right? Because this is just a property, basic less than high school properties of rational numbers. And of course, this will imply that the sum of Ki is equal to m. Okay, then what can we write? Okay, let us see. So we can write that A1 P1 up to AN Pn, this can be written as A1, of course, we just write K1 over M up to AN Kn over M. Okay, and this is what? This is A1 repeated K times, okay, K1 times. And then we do the same for A2, A2 repeated K2 times, and so on, until we have AN repeated Kn times, and the whole thing is to the power 1 over m. Okay, so I just rewrote. So what do we notice now? We remember that the K1 plus K2 up to Kn is equal to m. So we have exactly m terms 1 over m. So we can apply the standard AMGM inequality, so the one that we have already proved, and then we would have that this is less or equal than the sum of all AI, the sum of all A2, the sum of all AN. How many AI do we have? Well, we have K1, right? So we have K1 A1, we have K2 A2, until we arrive at Kn AN, and we divide by m. Well, but K1 over m is P1, K2 over m is P2, so we just have sum of Pi AI. Okay, so the case where, so sorry, there is a question, a couple of questions. Are the Ki rational? Well, of course, but they are natural, as a matter of fact. So there is a comment that seems so, a question, so maybe I didn't explain properly, but I mean by this the composition as a fraction, a standard fraction, so natural above, natural below. Okay, So that's what we get in case one, where all the PIs are rational. But when we pass from here to here, we know exactly that by the case that we have already established, that we have equality. Sorry, maybe it is better if maybe I will read the question when I finish the proof, okay? Because otherwise it's gonna take 1 hour just to answer the questions. I will finish the proof, then I will answer the questions. Okay. So with the case of equality here is when all these numbers are equal. So in particular, when A1 is equal to A2 is equal to AN. Okay. So once we have done this, we can move to the case where P is in Rn. So, and the idea, as I said, is to exploit the fact that Qn is dense in Rn and the continuity. So, and now there is a little bit of an issue that maybe I would like to mention. So it will be, let's say, relatively easy to say now. Let us take Qk, so a sequence Qk, which converges to P in Rn, where Qk belongs to Qn for all k. Okay, so k is just an index. So this means convergence as k goes to infinity of this number, of this sequence to this vector in Rn. Okay. However, here, if we want to use the version of the inequality that we have just established, we should make sure that this sequence this sequence Qk is such that the sum of Qki is equal to 1. So in fact, we could do this. It is not a problem really to construct this approximating sequence. I would suggest you to try to prove that in fact you can always do this. But in order to avoid this step, just to make the proof self-contained, I will use the version of the inequality where the weights are not normalized to 1. Okay, so for this, I remember that if the weights, for now rational, not normalized to 1, then we have the following inequality, which is actually quite easy, and it is the one that I suggested you to have a look at. So the only difference is that now we have to take the power 1 over the sum of the pi, and here the difference will be that we take the sum of the pi but we have to divide by the pi. Okay, so this is the version of the inequality, sorry, not equal, but less of equal, when the weights are not normalized to 1. So we can apply this inequality to our situation, and let's see what we have. So let us consider we have the sum of the AIPI. Of course, in our case, the sum, I don't need to write this exponent because I already know that this exponent is equal to 1, but I'm going to use this. So this can be written as the limit for k going to infinity of the product of AIQKI, and now I need to do 1 over the sum of the QKI with respect to I. Okay, so we have this. I'm just using continuity at this point, and now I use the fact that the limit respects the sign. So I have limit with, I take this inequality now. So I write sum of qki over sum of qki. And what we get, well, this is, again, by continuity, this is entirely trivial. So we simply have that this converges to the sum of the pi's, which is 1. So we are left with pi ai. So now the real problem is that when we don't have the limit, we can really say that equality here is true if and only if all the i's are equal. But if we put the limit, we cannot say that anymore. So we have to recover this in some other way. And the way to recover this is by observing by the following observation, which is quite interesting, and it is this. So we decompose each pi, we decompose it in a pi prime and a pi double prime. Okay, and we want that the pi prime are rational. And once we have this, then clearly we can write that the product of ai pi, this can be written as the product of the ai pi prime and the product of the ai pi double prime. Okay, like this. Why do we do this? Well, because the idea now will be, first I estimate this, and I know that the estimate of this, since the exponents are rational, I will have equality in this inequality, in the inequality for this term, if and only if the elements are equal. Okay, and in this case, I have only the less or equal inequality. But then if I have strictly less and less or equal, if I want to have equality here, I need to have that I have equality here. So in particular, this means that I will enforce again that the AI needs to be all equal in order to have equality in the AMGM inequality in the case of rational exponents. There is a trick, however, because you see that, well, you don't see it yet, but you will see it in a second. It actually, let's call it a fortunate coincidence rather than a trick or an effect of the construction. So let's see what we can say. So remember that I split this part that I want to estimate by this term and this term. Now I have the same problem as before, that the sum of the pi is not 1, so I need to use this version. I need to use this version of the estimate. Okay, so let us see. We get that the product of ai pi prime, then I need to take the sum of the pi prime. This is less or equal than 1 over the sum of the pi prime, sum of pi prime ai, and there is equality. There is equality if and only if all i's are equal. In this case, we can claim it without any problem because p prime are rational. Then, in the case of the p second, we have the same inequality, but we cannot say anything about the case of equality. However, this doesn't bother us at all. We have this pi second, sum pi second ai. Okay, so we cannot say anything about the case of equality, but this really doesn't bother us. Okay, now in order to combine these estimates with these estimates, I will do something quite trivial. So I will just move this to the other side. Okay, I will move this to this side, my prime, and I will move this to this side. So I raise to the appropriate powers in order to have this expression. And now now I can put together these two inequalities to write the following, that this is the product of these two is less or equal than the product of these two, pi prime, sum pi prime ai to the sum of the pi prime, and 1 over sum pi second ai to the power 1, no, sorry, to the power sum pi second. Then I'm still not at the final result, because I need to, I want to get a sum involving the PIs. Well, but now looking at this, it is very natural what we are going to do. We are just going to do again an application of the AM-JM inequality with this exponent and this exponent. Okay, but we have to be careful here, because we are after the equality sign. So so we want to make sure that we get the right information about the equality sign. So for that to be possible, we need to have that both this and this are rational, because only in that case we have a precise identification of the equality sign. But this is in fact true, because look, we have that the sum of the pi, the sum of the pi is equal to the sum of pi prime plus sum pi double. But this is one, which is rational. This is rational because sum of rational, and therefore the sum of the pi second is also rational, because it is the difference of two rational numbers. So we are in fact in the situation where we can use it. Moreover, the sum of this and this is 1, so we are in the perfect case for the AM-JM inequality, and this means that we have this, so this exponent pi prime multiplied by this part, which is 1 over sum of pi prime and then sum of pi prime ai. So this simplifies with this, and the same thing here. So we see that we got the result. So pi second 1 over sum pi second and sum pi second ai, which is nothing else than sum of p prime, sum of p second multiplied by ai, which is nothing else than sum of pi ai. And now what can we say? Well, we have equality in this step if and only if the sum, if and only if this term and this term are the same. Okay, but then let us backtrace. So we have here, we have equality if and only if a1 is equal to an. Okay, so in order to have equality, we need to have equality here, we need to have a1 equal to an. But if we have a1 equal to an, of course, the sum of p prime a is equal to the sum of p second a, and then, sorry, the normalized sum are equal, not the sum themselves. Okay, and therefore we have that we have identified the case of equality in this situation. Okay, so this idea, the first time I saw it, I thought it was very smart, and I don't think I would have had this this intuition very quickly. So I particularly liked this proof. Okay, so now really we are done. We have the full proof of the AM-JM inequality. Okay, I want to give another proof. So this that highlights. So maybe I give a sign here. I give a sign that the proof is over. So we completed the proof. This proof was perhaps the first proof, and it uses very interesting arguments, and this is probably its main reason of interest. There are other proofs that are simpler and quicker, but let's say slightly more sophisticated, in the sense that they use perhaps basic results of calculus. And maybe one of the most famous ones is a proof due to Polya. So let's say another proof of AM-JM, and this is due to Polya. And the legend says, maybe it is not a legend, maybe it is, I don't know, that he saw this proof in a dream. So now when we see the proof, we will see that in fact perhaps there is a rather oniric component to this proof. But so the proof is based on so it is based on a very simple inequality, which is just inequality 1 plus x less or equal than e of x. And as a matter of fact, we even know where they are equal, right? This is one of those things that, again, you learn in high school. It is just the fact that that you can verify in many ways. For instance, by calculus, that we have that the exponential function here. There is it has a tangent with slope 1, and 1 plus x is this guy, right? And they touch exactly at the point 0. Okay, at the point 0 there is a tangent point, and in all other points the function e of x lies above the function 1 plus x. So this is probably the point where Polya had his dream, but of course, if you think a bit, at least in terms, what kind of tools should I use in order to approach the AMGM inequality? Well, the AMGM inequality bounds a product by a sum. So whenever you try to convert a product into a sum, you should always think about, maybe I could try something with exponents and logarithms. So from this point of view, there is something reasonable in this approach by Polya. So reasonable in the sense that it was not just purely a dream. So first, let us start how we could approach this. Well, first we see that maybe it is convenient if instead of this we write that x is less or equal than e to the x minus 1. Then we start thinking, okay, we want to apply this to powers of ai, powers of ai to the power p. So okay, so maybe we could write this. We could write that each point ai, each number ai, is dominated by e to the ai minus 1. And then clearly this implies that if we look at ai pi, this is dominated by a pi ai minus pi. And then we see that, well, okay, now at this point we have a way to bound the product. So the product of ai pi is less or equal than of course the product of what we have on the right hand side, which is pi ai minus pi. But then this is simple because we use the properties of the logs, and we just write that this is the exponential of the sum of pi ai minus 1 because we have minus p1 minus p2 and the sum of them is 1, so we just write it like this. Okay, so we start having something that we like, because it is possible that we can do something to this guy. Well, first of all, we have this basic inequality, so exponential of sum of pi minus 1, and we know something about this. So this is larger or equal than the sum of pi ai, right? But this is not very useful because we are doing. This is bounded by this above, but this dominates this. So we don't like it very much, right? Because it does not go in the sense that we want. It would be ideal if it were less or equal, but of course it is not true. Okay, so here it looks like we run into trouble. Then we start thinking again about all the, let's say, our toolbox, and our toolbox says, well, we didn't use that the inequality is homogeneous. So let us do a normalization then. So we take Z, we define Z as the sum of the PI and then we define a hat I, we just normalize. So we take AI over Z. What does this imply? Well, this implies that certainly the sum of the PIAI hat is equal to 1 just by normalization. And therefore, we can apply one of the inequalities that we have just established, so this inequality, right, to say that the sum of the PIAI hat is less or equal than the exponential of the sum of PIAI minus 1. Oh, but now we like this. Why? Well, because this guy is equal to 1. So this is exponential of 0, it's 1. Yes, okay, this is actually the trivial part. The interesting part is the following one. The interesting part is this one. So that this bound is, this quantity for the I bar is dominated by this quantity, which is 1 for the I bar. So this is the trivial bound, actually, sorry. It corresponds to this. There is nothing new here. I did the wrong one, sorry. So the real one, the real interesting one is this one. This one that is dominated by the same quantity. So remember that what I did here was for arbitrary A. So I can replace A with A hat. Okay. So then we have here sum of PI A hat I minus 1, which is indeed 1. Okay. So I have that this is dominated by 1. At this point, I'm sure that you already imagine what we're going to do. We are simply going back to the A's, right? So it is.
Shouldn't the PI be on the exponent, on the product?
Yes, I'm sorry. You're right. I'm sorry. Yes, you're definitely right. Sorry, I just copied wrongly.
No problem.
Sorry.
Thank you.
Sorry for the typo. Okay, now you imagine what we are going to do. We are just going to substitute a hat with its definition. So maybe it's short, I can do it here. So we are going to get power of, so we have AI over Z to the power P. So we have certainly AI to the power PI, and then we have Z to the power PI, less or equal than 1. But then what is this product here? So this product here is Z to the P1 plus P2 plus Pn, which is 1. So this is equivalent to saying that this thing is less or equal than Z, correct? But Z by definition is this one. So Z is this. So we are left with less or equal sum PI AI. Okay, and this is the proof of the inequality. Now, okay, there is an issue here because the issue is, okay, but wait a second, when do we have equality in this inequality? Well, equality is going to be achieved by the equality condition, again, of the EM-GM inequality. And what is the case of identity there? It is A hat all equal. So, but A hat all equal, then this implies that we must have that all A hat are equal to 1. And in particular, this means that all A's are equal and are equal to Z. Well, of course, they are equal to Z. This is triviality, right? Being all equal, we just have here, you just take it out and you have sum of PI is equal to 1. So it just identifies the identity case also in a very quick way without any other, let's say, special effects, okay? Okay. this was to show that we have other proofs of the AMJM inequality that are very quick. I will now show some other arguments that I find particularly interesting. I don't think I have very much time, so well, okay. I will try to do the best that I can. So now, before proceeding, we will establish some properties of means that will be particularly useful to establish a proof of the AMJM inequality that is really a one-liner. So let's see how we do this. The core of the whole thing is a continuity property of the means at zero. So we call it a lemma, and we say that if we have a Rn plus, then we have the following. We have that the limit as r goes to zero of the mean MRA is M0A. So this says that the means, this mean operator, if you like, is continuous at zero. Okay, that's why I said that. So the proof is simple, but uses a little bit of calculus. So it is less elementary in the sense that it is, let's say, less algebraic than the ones that we have given so far, but it is particularly, it is not particularly hard either. So let us first remember what this means. This so I use this notation also when I use the weights, because I don't want to write all the time MRA of argument P, whatever. We just do the general case and we are fine. So R 1 over R. So, and our proof is going to use the properties of the exponential logarithmic function. And first we write this as exponential of 1 over R. And then we write the log of the sum of the pi ai r. Yes, okay. And now we use the expansion in Taylor series of the exponential function applied to this part here. Okay, so by this I mean the following. So we use the Taylor expansion. Notice that we use the Taylor expansion around zero, but in fact the exponential function is very nice because it is analytic. So even if we had a very large R, it would be fine. So we have we use the following. So we write x of R. We write it e to the log x r. And this can then be expressed as 1 plus r log x, plus then we have a term which I write big O of r squared. Okay, so it is r squared and higher powers. Okay, so once we have this, then we can, I continue from here, we can express this as exponential 1 over r. And then we write log of 1 plus, so I do it for each I, and then I do the sum. Okay, so this is what I do. 1 plus R, sum of pi log ai, plus a term which depends on R squared. Okay. Now what we do, we need to pass to the limit as r goes to 0. So we need to take the limit as r goes to 0. And here we use the properties of the logarithmic function. So you see that we have log of 1 plus r plus something of higher order divided by r. And we know that in this case, the limit is just the coefficient of r. Okay, so this means that if we pass to the limit, we have that we get exponential, of the sum of pi log ai, which is nothing else than a1 p1 A, N, P, N, which by definition is M0 of A. Okay, so we have proved that MR of A converges to M0 of A when R goes to 0. Okay, this is the first tool. Then we have another tool which is completely elementary. It is now completely elementary because of what we did in the previous days. And so, if you like, we can see this as a study of the properties of the means. We will straighten it later on, strengthen it, not straighten it, sorry. We will strengthen it later on, but for the time being, this is enough. So another lemma is the following, that MR of A is less or equal than M2R of A. By the way, this answers one of the questions that we asked yesterday. So when we introduced the AMJM inequality, remember that we did this thing. So we said we have AB less or equal than 1/2 A squared plus 1/2 B squared. And then we said clearly, if we replace A and B with square root of A and square root of B respectively, then we get the usual AB less or equal 1/2A plus 1/2B. Okay, but at the same time, we also said that, well, but we can also take the square root, right? We can also take the square root, and here's the square root. So, and then we said, okay, we have two bounds. Which one is best? This is the answer. Okay, so the answer is that this one is better. This one is better than this, because always in a more general setting, as you see, so we are giving a much more general answer to this initial question, we have this. Now, I'm sure that you can do this in a second, because this is just the Cauchy inequality. Okay, this is the Cauchy inequality for sequences with weights that we discussed yesterday, and we said that you can do it either with the, let's say, abstract approach of the vector space endowed with an inner product, or you can do it also by hand, by splitting the P in square root of P on one side, square root of P on the other side, and doing the standard computation. Okay, so let me now give you a couple of quick applications of this result, and in particular there is a proof of the AMGM inequality that I consider absolutely wonderful. So I will give you applications of the previous lemmas, so of the lemmas to AMGM. So this is page 6. So the first application is to the equality proof in the AMGM inequality. Okay, so remember that the equality proof required quite a bit of effort in the first proof, in the algebraic proof, because we needed to split P in a rational part, rest, and all that. Okay, let us see how we can do it with the simple arguments that we have just developed. So first of all, we have that M1 of A, so the standard mean of A, is larger or equal than the mean of order 1/2 of A. We are using the lemma now. We are using this lemma. Okay, so when R is equal to 1/2, MR of 1/2 is less or equal than M1. M1 is the usual arithmetic mean. Okay, and also we have a case of equality here. We know very well that the only case of equality here is when all the A's are equal. So let us keep this in mind. Then by very trivial manipulations that I ask you to check that I'm doing correctly, this is exactly the same as writing that this is M1 of A, M1, sorry, not of A, but of A 1/2, but then taking the power 2. And now we use the AMGM inequality in the, let's say, non-sharp form. So we simply say larger or equal. We don't care about when is the case of equality. No, this is, for now, it's not relevant. And this is then M0 of A to the power 1/2 squared. But again, M0 of A to the power 1/2 squared, this is nothing else than writing M0 of A. So look what we have. We have one situation of larger or equal and another situation of larger or equal. Notice that we have exactly gotten, well, we didn't get it as a proof itself because it depends on the larger or equal proof. We are only after the equality case here. So here we have larger or equal. Here we have larger or equal. It is clear that if we want to have equality between this term and this term, we need to have equality here and here. So here we don't know. But we know precisely that here we have equality if and only if all the i's are equal. Then conditional on having equality here, so which means assuming that all the i's are equal, we know exactly that in this case also we have equality. So we have identified the case of equality in the AMJM inequality. Okay, so this is the first, and now the second application, which is the most striking, I believe, is another proof. So it is another proof of AMGM. Unfortunately, I forgot who gave this proof first, but it is a wonderful proof, really. It is so smart that it is very simple and very smart, really beautiful proof. So this simply says, okay, M1 of A is larger or equal than M1 half of A. Okay, but then why do we stop here? Let us continue. This is larger or equal than M1 fourth of A. This is larger or equal than M1 eighth of A, and so on and so forth. And so then you immediately guess what we're doing. This is larger or equal than M1 over 2K of A. And then we let K go to the limit. And we use the first lemma that we gave. So we use this lemma, the continuity of the mean at 0. And we have that this goes to M0 of A. And that's it. So that's the proof. So as I said, it's a one-liner. And of course, the natural question comes, well, okay, wait a second, because we have limits here. No, there is no problem, because if we want to have equality from here to here, we need to have equality in this chain of inequalities. So the only way to have chains of inequalities here being equalities, it is just by each one of them. It is sufficient to look at just one of them. So all the A's must be equal. So A1 must be equal to A2 up to AN. Okay, so the argument is just that all inequalities are strict unless all the i's are equal. Okay, so that's the argument. So it's a very simple, very beautiful argument. Of course, it relies on the continuity of MR for R going to 0, but nonetheless, it is particularly quick and sharp argument. Okay, I was planning to talk about some consequences of the MGM inequality, but I think I won't do that. Instead, we will move to starting to ask ourselves some other questions that are entirely natural, and these will lead to another family of very important inequalities. So let us start from Cauchy. So we start again from Cauchy, and we just start from the easiest case of Cauchy. The easiest, let's say the simplest. And of course, then we also wrote it in this form, which is exactly the same. But maybe now it is better if I write it like this, because this is particularly interesting now. And now we ask ourselves, is there anything special about these numbers 2 here and these numbers 2 here? Can we perhaps have something with different combination of numbers? This is, of course, an entirely natural question, because it may happen that we are trying to find a bound on a product when we don't know that this sum of squares is finite. Maybe we know that the sum of the power 4/3 is finite, but we don't know about power 2. Power 2 is too much. Can we do something? Of course, this is a very natural question to ask, and I would like to show some ideas to do this or to approach this issue. So a natural and I believe in this context almost forgotten or ignored idea is just to do what Cauchy did in the proof of the GM inequality. So he just iterated. He said, I cannot do iteration on the naturals, but I can do iterations on the power of 2. So what does that mean here? Okay, let's have a look. So now I beg your pardon, but I need to change notation in the sense that I will hide the indices of summation. So this expression means summation of AI, A1i, A2i, A3i, A4i with respect to an index I. So I cannot write millions of indices, so you know what I mean, okay? And also I don't want to write A, B, C, D, because if I have too many, then the letters of the alphabet end at Z, and I may have more than that. So let us then proceed just using what we have. And of course, this is what? Well, this is less or equal than the sum of AI, A1, A2 square to the power 1/2, and then sum of A3, A4 square to the power 1/2. Then we ask ourselves, well, but let us collect. Let us do the same thing again. So this guy here, how can we write this guy here? So this guy is of course A1 square, A2 square. So it is the same. I put it inside because it is easier to look what we're doing. And we apply again the Cauchy-Schwarz inequality here. So we would have that this is sum of A1 square, which is to the power 4. And then we would have to write to the power 1/2, but there is a 1/2 outside here, so we have 1/4. And then we do the same. So for the second guy, we have 4, 1/4, and then 3, 1/4, and then we have 4, 4, 1/4. So, and this looks interesting, but of course, it is not yet, we are not even near to changing powers here. We are only adding terms to this summons. Okay, but let us not discourage ourselves. Let us proceed. By the way, you see that this is the same as writing A1 to the power to the norm L4, A2 at the norm, evaluated norm L4. By the way, we proved that this symbol L2 is a norm, but what about L4? We haven't yet proved it. Okay, sorry, I see that I'm running over time. What time is it? Yes, I will leave 5 minutes for questions because anyway, there are always not many. So just 2 minutes and then I will stop. Then A3, L4, A4, L4. So now the observation is that we can iterate this, and this is absolutely not difficult. I won't do it. So I will just sketch this argument and then I will give another argument, a complete argument next time now. So then here we get that we can get the following, that if we iterate, so we have power 2k, this will be less or equal than A1 to power to the norm L2k up to A2k L2k. Okay, for now I'm using this norm notation only for parsimony of notation. Okay, so as a quick notation. Okay, now you understand now where I'm going. Now we have two steps that we need to try to do. Questions, let's say. We have questions now. Question 1. What if we have a number of terms? So what if we have A1, AM, but M is not 2 to the power k? And then question number 2, what do we do if we really want to replace the norms here from natural numbers to real numbers? And so now you kind of guess that the idea is to move first to rational numbers and then from rational to real. So the idea is similar to the proof of the Cauchy inequality, but not of the AMGM inequality, sorry, but it is not the same. However, this is doable. Okay, I will write the details in the notes, but I want to do it neither today nor tomorrow because of lack of times. I just wanted to give an idea of the fact that we will arrive to the following thing, and then I stop, sorry. So this is A1 LQ1 up to AM LQM, where we need to have that 1 over Q1 plus 1 over Qm will be equal to 1. Okay, so it is possible by these steps to arrive at this inequality. This inequality is called the Hölder's inequality. It is the Hölder's inequality for sequences. And what is the very interesting fact that this proof shows is that Cauchy, Schwarz, actually Cauchy only, the Cauchy inequality implies the Hölder's inequality. So this is kind of let's say surprising, but that's how it is. Okay, sorry for going slightly over time, but I know that you have the lunch break after me, so you still have anyway 4 or 5 minutes for possible questions. So maybe I will read if there are any questions.